Good afternoon, everyone. My talk is related modeling shipping sound analysis for European waters, also including past years, starting from 2016 to 2023. Also, we include forecasting of the shipping noise for the future years up to 2050. And first of all, I would like to thank my co-authors from different departments of the Ch2 in Germany, UK, and Canada, also Maritime Institute of Netherlands, and EMSA for sponsoring this work. Shipping is one of the largest sound source in the European waters. Therefore, it is critical to know what is its contribution to ambient sound together with wind, and also predicting how this ambient sound changed by time for the past years and also for forecast years. For that reason, it may be relevant to CTBTO's historical data set and also future location for the new measurement stations to know what is the ambient sound for the different regions. So I would like to present how we did this approach for the European waters, but the same framework can be applied for any location in the world. And what we did for this work was just calculating sound maps for the shipping noise based on the Marine Strategy Framework Directive of the European Union. And what we see from these sound maps are hotspots of the shipping sounds, their locations. Also, it helps to understand how the time trend change in frequency components. Also, it helps to minimize this noise, mitigate this noise for noise critical areas. And today I will show some examples from the recently completed project Navison, funded by European Maritime Safety Agency EMSA between 2022 and 2024. Our goal was for this project to calculate sound maps only for two frequencies, at 63 Hz and 125 Hz. They are the descriptor 11 desiccated frequency bands described in the maritime described in the MSFT regulations. And at the start, we need source levels of each ship categories in the European waters. And to do that, we had a new source model piano, including separate components for cavitation noise, machinery noise, and different mitigation measures to understand how this noise can change for the future years. We focused on 5 different vessel categories listed here for cargo vessels, containers, passengers, also tankers, and roll-on, roll-off vessels. And sound maps and sound energy densities are calculated for these categories in the European waters. As a summary of our framework, we start with the AES data for ship tracks. In addition to AES data, we need ship particulars to know what are the ship-specific properties to be used in the source model. And using this information separately for machinery and cavitation components, we had source levels for each ship, and they are validated with the ECO program of the Canada with some comparisons, as I will show in the next slides. Then we get information from the European database like EMOTNet and Copernicus for different environmental inputs, and combine everything with the Artemia sound propagation and sound mapping model to get the sound maps for different vessel categories, different time periods, different frequencies, also different forecast scenarios, which may be relevant to forecast. This slide shows an example, a comparison between piano model and measurements from ECO program. At the same time, you can see other source models like Jomopan's ECO model and Wittgenstein model. They have all good agreement for containers. But what was the benefit of the piano model was seen especially for the cargo vessels, like in this slide. We can predict this low frequency hump more accurately with this model, and it was critical for our frequency band. So we need for that reason, we needed a new source level model. And combining this source level model with the environmental data set, as I mentioned, for bathymetry and sediment information from the EMOTNet, and also getting sound speed profiles for different modeling region from Copernicus. We use them in the parabolic equation model to calculate propagation loss, then we get sound maps. And the sound maps were calculated for different vessel categories. Here you can see they are like represented in the JS software for different categories like tankers, containers, passengers, and some of everything in the picture on the right. And as a result, we get quite large number of the shipping map layers. It was more than 2,400 for the past years, and it was more than 1,800 for forecast scenarios, so it was quite difficult to understand. And so we were wondering, is there a simple way to analyze this data, to understand what is their time trend, or what is the contribution of different vessel categories, as a complementary metric to sound maps. And can we quantify the sound maps even with a single number? It helps to management of the shipping sounds if we get very simple numbers and follow time trend with this number. To make it work, as mentioned in the previous slide by Michael, we use also sound energy calculations, but we use mostly sound energy density. What we did is like we sum everything in the x, y, z direction of the sound maps, divide by rho c square, we get the total sound energy. And if we divide them with the volume of the seawater, we can get a universal quantity for comparing what is the time trend of the shipping sound in the different European waters. It also helps to understand what are the contributions from the different ship categories, because it's a linear metric and it's quite easy to visualize as well. So if I show the results, what we get for different locations, on the right we see sound maps for Baltic Sea, also for North Sea, for Northeast Atlantic, Mediterranean Sea, and Black Sea. We can see main shipping routes here, these maps, and it's for 63 hours, and we can identify what is the most noisy location. For instance, English Channel was one of the loudest locations in this map, also North Sea and Baltic Sea. But we cannot see clearly what are the contributions from different vessels. So if we calculate sound energy density, like in this plot, we can suddenly see that like blue ones, cargo vessels are making the largest contribution. Second, we can see tankers, green one making second largest contribution, and the ro-ro vessels making third largest contribution at 63 hours. And we can see the time trend. For example, if you look at the 2020, we can see decrease in the shipping sound energy, and it's coming from the COVID. And after that, we can see increasing noise for all European waters. It's based on the information what we see on the map on the right. And if you look at other frequencies, we can see totally different pictures. So here we see ro-ro vessels are making second largest contribution, very close to what we get from the cargo vessels. So it saves this kind of information from the sound maps. And again, like we could look at these maps instead of sound energy density, but it's quite hard to see all details and different time trends. But it saves also different information than what we get. So we need both of them to analyze our results. And for each different location, for Baltic Sea and for the North Sea, we can see similar time trends, but when we look at the Mediterranean Sea, we can see increasing time trend comparing to other ones. So for each location, we can repeat the same calculation to understand what are the local contributions, what is the local change, and which ship category is the loudest in each location. And they were the results for the past years, but also most may be interesting for the CTP tools analysis to know what is the noise in the future after implementing some mitigation measures for the ships to make them quieter or make them more efficient or less greenhouse gas emissions. So we had 4 different scenarios for this forecast modeling. We start with the standard, like business as usual model, just increasing the number of ships for each year, and greenhouse gas emission roadmap. Also, it has different mitigation measures, and we also have urine management isolation, and some of them in the 4th scenario. And to make them, we start with the baseline scenario. We calculated each mitigation measure separately with a 100% penetration of these mitigations. And combining them with the probabilistic approach, we can get this information from the IMO guidelines or different literature, different paper from the literature, and we can estimate what could be the reduction in the future. For example, if you look at this map, we see the results for 2050, and we can see around 5 dB reduction for the Baltic Sea if all measures are implemented as a combination. And again, we can calculate sound energy densities for these maps. We can increase for the business as usual scenario. And if we look at other scenario, we see totally different pictures for each ship category. For example, the second one was for the greenhouse gas emission scenario. we can see even increase for some categories. Even we reduce to greenhouses, we cannot reduce the noise, we can increase like we see in the tankers in this picture. But for other scenarios, we see more decrease. And they are the results for 63 hours. And for other frequencies, again, we can see different mitigation performances. And it's a different representation of the same graph to show how many percent reduction we can get for different vessels. And again, we can see most of the categories decrease except tankers in the greenhouse gas scenario and containers. And it can say us some information about what can predict for different years by repeating the same scenario with different mitigation measures. As a conclusion, understanding time trends of the ambient noise is critical, and modeling of the sound maps with a standard framework which can be valid for larger location is quite helpful to understand what we can expect in the future and what was the noise in the past years. This type of modeling scenario is not limited only Europe, and it can be applied anywhere in the world. So it can be even relevant to CTB2 measurements in the Pacific Ocean to characterize what we saw in the previous years and what we can expect in the future years, and combining them with the measurement help to understand and interpret data better. And I would like to thank EMSA as well for funding, and for any questions, you can contact Sami as a project director. And thank you for your all time and listening.
Thank you, Oskan. Questions from the room? We have one online question. Although relatively uncommon, under which category did you place seismic survey vessels and other research ships that intentionally generate noise for data acquisition purposes and are mostly active in North Sea during summer season?
Actually, we didn't include individually seismic surveys in this work, but they were included in other calculations to compare, but it was very limited, I think, for this type of comparison. We only focus on 5 categories to get some information.
Okay. So, more questions? So I have one. So, but it's easy to also include other type of sources. Or what will be the main limitation? Frequency? Or?
I think if we know the source level, we can use a similar approach for any modeling. Especially for low frequencies, we can keep using the parabolic equation model, but if we need higher frequencies, of course, we need more computational time-efficient propagation models. It's the only limitations, I think, what I can say.
And now that you mentioned how long it takes to perform a study like this, from the computational point of view?
We use high performance computing for the calculations, so it took like more than a month, I think, to make all calculations at different years and different categories. But it was indeed like quite computation intensive for the calculations.
Okay, thank you. So if we have no more questions, so we can close the session?
Yes. Thank you very much to everybody. It was very good.